So in this question here, we're going to go through the process of graphing this natural log of 1 plus x, and the whole thing is being squared. Okay, so this time the square isn't within the log, it's outside. All right, let's jump right in. Let's start where we've been starting the last few questions here. We'll start with the domain. Remember that we need to be taking the natural log of a positive value, so we're going to insist that 1 plus x is greater than 0, and what that means is x has to be greater than -1. So there's my domain. Okay? Now, next thing we want to take a look at here are the intercepts. I'll do that down here this time. Intercepts here. And again, I'm going to grab the low-hanging fruit first. So the y-intercept here, y is going to equal the natural log of 1 plus x squared, except replace x with 0. I probably should have done that right away there. 1 plus 0 is 1. The natural log of 1 is 0. Squared is going to be 0. So our y-intercept here is going to be 0. Now, as a result, I know that if the y-intercept is 0, this means that one of our x-intercepts is also going to be 0, because I know that means we're going to the origin. And we'll see that in just a second here. So we'll let y go to 0 if we're going to look for the x-intercept. All right, now I'll take the square root of both sides, but that's easy. The square root of 0 is just 0. All right, now we've got a logarithmic equation here. Let's convert it to exponential form. So e to the 0 is going to equal 1 plus x. That's going to be 1. Subtract 1 from both sides, and there you go. There's my 0. So my x-intercept, my y-intercept. So we know that it's going through the point 0, 0. Okay, so at least we've got 1 point on the graph. Good. 4. Okay, let's take a look at asymptotes. Well, in this case here, think about what a logarithm looks like. The asymptote, the vertical asymptote occurs, okay, when the argument of the logarithm is 0. So if we take that 1 plus x, set that equal to 0, we're going to get that vertical asymptote at x equals -1. Okay, which is consistent with what we just saw here. We knew that there was a boundary to the domain, and that boundary is going to be an asymptote. Finally here, oh sorry, that should have been 3. Here's 4. 4, we're going to take a look at where the function is positive and where the function is negative, where it's above the x-axis and where it's below the x-axis. So to start off with, we're going to set that function greater than 0. Now we already know the domain. We know it's got to be greater than -1. So what we're interested in here is where that thing is greater than 0. Well, now that's an interesting result right there. Because if I take the square root of both sides, if I'm trying to figure this out here, the only time that this won't be greater than 0, oops, sorry, the only time that this thing won't be greater than 0 is when it's equal to 0. Other than that, if the natural log, the natural log of 1 plus x takes on a negative value, that square is going to make it positive automatically. The only number that doesn't work here is when x is equal to 0. When that function is equal to 0, and we already know that that happens at the origin. So this really, without me putting too much effort into it, I know that it's going to be greater than 0, essentially where x is greater than -1, and x doesn't equal 0. Because at 0, the y-coordinate was 0. Other than that, every other place, this is going to be positive here. It's never going to go less than 0. So anyway, that was kind of a quick, easy one to deal with just because of that square around the whole thing. Kind of like that. Makes my work easier. All right, now let's go down to where the fun really begins, considering the course that we're in. Let's take the derivative. Let's figure out where this thing is. Oh, sorry, put a little title here. Let's figure out where this thing is increasing and decreasing. So here's our original function. Now what we're going to do is take the derivative of it. So there's a chain rule that's going to be in play here. So bring down the 2. This will be the natural log of 1 plus x. And then I'm going to multiply by the derivative of the natural log of 1 plus x, which will be 1 over 1 plus x. And then the derivative of that would be 1. So I can leave it right there. So now I'm looking for critical numbers to start off with. Okay, And so my critical numbers are going to occur when the derivative is either 0 or undefined in the domain of the function. So now it's going to be undefined at -1, but I don't get -1 in the domain of the function, so that's actually not an issue. That's not a critical number. That's still an important number when I'm looking at the intervals. I'm going to use it, but it's not a critical number. Okay, it's not, that isn't a possible max or min. So the real issue here is where 2 times the natural log of 1 plus x is going to equal 0. That's really the only place that this can happen. So I'm going to divide by 2, and nothing's going to happen. The 2 is just going to disappear. So I'm going to be left with this exponential, and I'll have this logarithmic, which I will convert to an exponential is what I meant to say there. So this will be e to the 0, so 1 plus x is going to equal 1. X is equal to 0. Well, that is interesting, because what that's telling us here is that point, 0, 0 that we found, that xy intercept there, that's the critical number. That's probably a max or a min. Now let's investigate the intervals here and just check this out. Okay, so we already know -1 doesn't work. Okay, and in fact I'm going to cancel it out here. I'm going to put an open circle on -1 because I don't even get to -1. And then I've got 0 out here. And let's just take a look at what happens with our values here. If you choose a number between -1 and 0, well, the denominator is going to be positive. So like if you put like -1/2 in there, 1 plus -1/2 is going to be positive 1/2 here. Okay, so that is going to be positive down there. Let's take a look what happens here. If I've got 1 plus -1/2 in there, okay, that's going to be 1/2. Now I can take the log of 1/2, but because it's a fraction less than 1, the result here is going to be negative. Think about what a natural log looks like. Okay, here's 1. If you plug a number into a logarithm that's between 0 and 1, you're going to get a negative value. It just naturally does that. So the numerator here is going to become negative. The denominator is going to be positive. So over here, this will be negative. That gives me an indication that the function is decreasing on that interval. And now if you choose a number bigger than 0, let's say 1, because we're lazy and 1 is easy. 1 plus 1 is 2. Well, that's not a problem. 1 plus 1 is 2. And the natural log of 2, because it's a number now bigger than 1, is going to become positive. So the whole thing is going to be positive over here. So we know that this thing is going to be, let's say, decreasing on the interval from -1 to 0, and I'm going to include 0. Okay, I can't include -1 because it's an asymptote, but I include 0 because it's a critical point, critical number, so it's going to either be a max or a min or a point where things level out here, but either way. This thing is going to be increasing on the interval 0 out to positive infinity. So I can see right now, because that 0, where x is 0, is the end point of a decreasing sequence and the beginning point of an increasing sequence, therefore I'm getting a min, and I already know the full coordinates are going to be 0, 0. I'm getting a min at the origin. Okay, there we go. Good, let's keep going here. So that was 5, so let's go on to 6. This time we're looking at concavity. So we got to take the second derivative. So y double prime, and because you can see this on the screen right now, I'm just going to leave it like that. I'm going to probably use the quotient rule for this. So the derivative of the numerator is going to be 2 over 1 plus x. Because that's really just the derivative of the natural log that I want. That's going to be 1 over 1 plus x, and then multiplied by the derivative of 1 plus x, which would just be 1. And then I'm going to multiply by the denominator, 1 plus x, and oh, I got to say, I really like what I'm seeing there. We'll get to that in a second here. Minus the numerator, multiplied by the derivative of the denominator, which is just 1, and again, I'm really liking that, all over the denominator squared. Okay, well, 1 plus x or 1 plus x, that's going to cancel. Now that's only going to cancel so long as we don't allow x to be -1, but we don't. Okay, it's not part of our domain, so that's not even an issue, so that's going to just kind of disappear there. Minus 2 natural log of 1 plus x over 1 plus x squared. That's about as good as I need it to get right now. I should be able to grab out pretty easily anything I need from that. What I'm looking for now are points where the second derivative is either undefined or 0 in the domain of the function, And these are going to be either points of inflection or cusps. Now I'm going to assume we're looking at points of inflection until I can prove otherwise. This thing is undefined when x is equal to -1. But again, yoink, that is not in the domain of the function, so I don't consider that a possible point of inflection. So I got to look at where the numerator could go to 0. So 2 minus 2 natural log of 1 plus x equal to 0. Let's bring the log over. So 2 is equal to 2 natural log of 1 plus x. Some of you might be wondering why I didn't get rid of the 2 to begin with. Yeah, it doesn't matter. I could have divided that out earlier. I'm going to divide it out now. Either way, doesn't make any difference. Now that I've got it down to a single logarithm, I've kind of cleaned that up. I'm going to convert this to the exponential form. So e to the 1 will equal 1 plus x. And so x is this interesting e minus 1 value. Okay? That's kind of a neat number that we're looking at here. So let's take a quick look at the number line. That's the only one that popped out, by the way. So here's -1. Nothing to the left, and I'm not including -1 in my interval here. The number that I've got here that's interesting is this e minus 1 over here. Okay. Now let's take a quick look here. To the left of that, okay, now bear in mind e minus 1. E is like 2.71 blah 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 blah. So subtracting that is going to be 1.7 something. So that kind of gives me an idea of what the values are here. So I could very easily choose 0 out of that, and I would be safe here. So if I plug 0 in to my second derivative here, 1 plus 0 squared is going to be 1, so that's not going to do anything. And if I plug a 0 up here, 1 plus 0 is 1. The natural log of 1 is 0. This whole thing quickly reduces down to just positive 2. Okay, meaning that what we've got here is a positive value. It's going to be concave up in that interval. Now if you choose a number bigger than e minus 1, let's just say e, for example. Okay, well the denominator is going to be positive. And now watch this. Because this number here is going to be necessarily bigger than 1, this natural log will be positive. Okay, and it will be, because it's bigger than e, well, okay, we should maybe take a bigger number in there because it'll make this make a lot more sense. If you threw in like a 10 in there, let's say, I think it'll be clearer because there might be a little bit of ambiguity because of the 2's here. If you threw in a number like 10, the denominator would be 11 squared. The natural log would be 11, okay, which should be big enough for you to realize that 2 minus 2 times the natural log of 11, because that's going to be bigger than 1, okay, and it will be bigger than 1 because the argument here would be bigger than e. Now, if that doesn't make sense to you, you're going to have to take a good look at the graph of the logarithmic functions here to get a sense of that. This is going to be negative as a result. So over here, we can write that out. So this thing is going to be concave up on the interval, not including -1, to e minus 1, but inclusive. Concave down from e minus 1 out to infinity. And again, we're going to include that, which means that we've got this point of inflection at e minus 1. Okay, well now I got to put that e minus 1 back up to here. So if I plug that in, e, the natural log of 1 plus e minus 1. Well, the 1's will cancel. The natural log of e is 1. Squared is 1. So there's my point of inflection. All right, now we've got everything we need. Let's sketch. Okay, let me give myself some room here. So we've got our coordinate plane. We've got over here, this is going to be -1, 1, 2, and I go out that far because I know where this is going to go here. Here's 1, here's 1. We know that there's an asymptote here at -1. Okay, now along the top here I'm going to identify a number line, and I'm going to identify where the increasing, decreasing changes. That's pretty easy to do because we knew that it was decreasing here and then increasing here past 0. Underneath it, I'm going to draw this number line here, and underneath it, I'm going to identify the concavity. Now, the concavity didn't change until I got to e minus 1, which is somewhere in here, actually. Let's just plug that in right there. This is e minus 1. And it was going to be concave up here, concave down over there. Okay, so I'll zoom back a little, back a little bit here. All right, so I know that it goes through the origin, and then I know it's going to go through e minus 1, 1. I know that I've got an asymptote here. It's decreasing and concave up, and that this is a min. So it's got to be doing something like this to there. Then it's it's increasing and concave up until we get to here, and this is a point of inflection, so it's not like a max or a min there. So increasing, concave up, and then once we get to here, it's still increasing, but now it's concave down. So now it's going to do something like this. Now, not like it's an asymptote. It's going to keep curving up like that kind of forever. So anyway, there you go. That's what the graph would look like.